I would like to introduce you now to Professor Dennis Kochmann, coming all the way from Caltech, and I mean it because he just landed after a very rough trip, but I think he's ready to land and give a plenary lecture. This is a challenge. Thank you very much, Dennis. Dennis is Professor Kochmann is a mechanical engineer. His PhD in Bochum, then he moved to Wisconsin, and then university, and now he's a professor in Caltech, and even though he has shifted from mechanical to aerospace, he defined himself as a computational material modeler, and his lecture is again going to round up a session, which I think so far is going to be great, and I'm sure this is going to be a great ending for that.
I hope so. Thank you very much for the kind introduction. It's a great pleasure to be here and to give this presentation on linking atomistics to the larger scales. All previous talks today have been on much bigger scales than what I start with. And so I'm going to tell you something about how we try to go from individual atoms to the bigger scales. And first of all, let me point out that this was done not just by me, of course, but by Jeff Ameling, Ishan Tembekar, and Gabriele Venturini, who all are or were at some point in time in my group at Caltech, with special thanks for collaborative support to our collaborators at North Carolina State University and my colleague Michael Ortiz at Caltech. And as Eugenio said, I should also say, in the spirit of U.S. commercials, this presentation is brought to you by Air Canada, who managed to get me here with a 28-hour delay right on time to give this presentation. So let's get started. I guess every one of us has a chart like this in one of their slides where we focus on what happens in plasticity across the various scales. At the lower scales, of course, we could do quantum mechanics and atomistics. That's usually way too expensive for what we are interested in. At the bigger scales, we heard very interesting ideas, the continuum length scale in the previous three talks. And then we have intermediate steps in the middle. So we have all of these techniques, and they're fantastic, but each of them resides at a very particular length and time scale. And so atomistics, for example, is what I'm very interested in because we don't need to care about elasticity versus plasticity. There's no Fe-Fp decomposition. Atomistics is extremely simple, and it comes from the lower scales. So put in a nutshell, atomistics, if you've never worked with it, is the simplest thing possible because there's only one governing equation in principle. We have a Hamiltonian system. The total energy is just the kinetic energy plus the potential energy. It's determined by the positions of your atoms and by the momenta of your atoms. And the governing equation really is F equals ma in the simplest sense. The force on each atom equals its mass times acceleration. And the force comes from the potential energy V. In atomistics, this potential energy depends on the positions of all of our atoms. And so what's very common from metals, and all of us or many of us are interested in metal plasticity, is the embedded atom method, which simply says that the energy of an atom depends on the positions of all of its neighbors, and so there could be a pair interaction, how am I interacting with my neighboring nuclei, and there's a second contribution that comes from the electron densities. And you simply sum up the energies for all of your atoms, and that gives you the total energy. Now we're solving F equals ma. You can either do this quasi-statically, you equilibrate the system, that's done with a relaxational solver, or we look at the dynamic evolution, you use explicit dynamics, your favorite solver, and that solves the system. Now, of course, we can do this. This is a very simple simulation which shows you void growth in single crystalline copper. We're pulling on this, and unfortunately the resolution is not great. But what you can see here in color code is dislocations running back and forth between individual voids. Unfortunately, the color is really not brought across well. You can see dislocations running back and forth. Each of these little points is an edge dislocation that runs. These are interacting. You can see voids grow, voids coalesce. This is of great interest, for example, for ductile failure, for spall strength, and so forth. Now, what's the catch? The catch is that this simulation is in 2D, because if I wanted to do this in 3D, I run into big problems. And Tom Hughes pointed out earlier, to go to the next slide, that computational resources, why is it not going? My apologies, I need to go to the next slide. No, sorry, it's a playing issue, so I'll just keep talking while I'm waiting for the next slide to come. The biggest issue is computational resources, and we all know that atomistics is very, very expensive. Why is it not doing it? Geez, I'm very sorry. Let me unplug and plug in again. Now it works. All you have to do is see what I'm seeing, and then we can go on. I'm so sorry. Here we go. So when we run atomistics, of course, we're limited by computational resources. So if we look at the computers we have, this is a collection over 10 years, the fastest computers we have in the world, and good computations run on those. And this is a prediction of what's going to happen with exascale computing, which is expected in the next 1 or 2 years. If we look at the number of atoms that we can model based on memory, we can see that we're fairly limited. Even if we believe future predictions, we can only model something on the order of 10 to the 14 atoms. For comparison, a cube with a 1 millimeter side length contains about 10 to the 20 million atoms. So this is fairly out of reach. We cannot model these big systems. And the second issue is, even though our computers are getting bigger and bigger, they're not getting faster. Everybody who runs explicit dynamic simulations knows that there is a time step constraint in terms of stability. We have the same here. The time step is femtoseconds, so if you want to model anything bigger than a microsecond, it's pretty much impossible. And so there's several ways to overcome this limitation, and one that I'm going to talk about today is to coarse grain atomistics. We do this in several steps. Spatial coarse graining is very related to the model order reduction scheme we heard earlier today. Ensemble reduction, which is the same as quadrature rules or similar to quadrature rules in finite elements. We will use adaptive mesh refinement. And finally, I'll briefly talk about upscaling in time. And all of this together will help us go to much bigger scales than what we normally do with atomistics. I would like to point out that this is by no means the only scheme that you can use to do that. There's a whole myriad of methods that have attempted to go across scales. And this is just a brief summary of things that have been done in the past. If you don't find your own method here, please just insert your name here. I apologize if I forgot anybody, because there are so many of these schemes. Now, what we do is very simple. Step number 1 is spatial coarsening. And here we borrow what's known as the quasi-continuum approximation to go from atoms to the big scale. And the idea is really simple. If you have an atomistic ensemble, and let's say each of these gray dots here is an atom, what I'm going to do is I'm going to elect so-called representative atoms. If there's a defect, if there's something interesting happening, I keep all of my atoms in the simulation away from defects, from cracks, from voids. I will coarsen, and I only pick a few atoms, which I call representative atoms, very similar to order reduction. What we do then is, of course, I still need to know where all the atoms are going, and so I use interpolation rules. You can use your favorite interpolation, the simplest one being an affine linear interpolation. We have used mesh-free methods. You can use different things. I don't think anybody has tried isogeometric analysis, so that might be an interesting field to try as well. But now what we've done is we've reduced the number of degrees of freedom dramatically from all the atoms in the simulation to just a few, the ones we want. And so our total energy now depends only on the positions and the motion of these red guys, and that's fantastic. Few degrees of freedom. The big problem is, in order to compute the total energy, I still need to visit each and every atom in the simulation, and that's extremely expensive. So why don't we do what you normally do in finite elements? We use something like quadrature. So this is what we have right now. We keep atoms only where we want them. We coarsen away. These are the nodes, or my rep atoms, representative atoms. On top of this, I'm going to select what I call sampling atoms, which are in the same spirit as finite element quadrature rules. And so people have done, in the literature, many different ways to do it. For example, you could pick one atom inside your element, compute its energy, multiply it by a weight. This is similar to first-order quadrature. You could use the nodes themselves. We use them anyways, so why not compute their energy, give them a weight? What many people do is use clusters around nodes for higher accuracy, or you can do combined quadrature where you use the nodes and some points on the inside. But in any case, what we do is reduce the complexity by computing only the energy of a few representative sampling atoms. This, unfortunately, brings about a big issue that we, I think, have a way to solve now eventually, and that is when you approximate the energy by only computing the energy of a few atoms, you're making a mistake, of course. That's an approximation. But this error, this mistake that you're making also manifests itself in the forces. If I now compute the forces on these representative atoms, they will not be exact because I made a mistake. I'm only considering the energy of a few atoms and not of all of them. Now what can happen is you can artificially find states where these 4 atoms have lower energy, but all the others have very much higher energy. This is an artifact, and so what this means is that the system can actually see forces which are absolutely not physical. And these are called spurious forces or residual forces. Just to give you one example, This is a scenario where I have full atomistic resolution in the bottom left corner, and I coarse in a way. This is a perfect single crystal where I would not see a single force in the undeformed configuration. And what you're seeing here are the forces which I computed in the undeformed configuration when I used this coarsening. So these forces just pop up. They're non-physical, and if you were to equilibrate that, you get anything but a realistic physical solution. It's just nonsense. So we can overcome this, and what we introduce is an optimal sampling scheme, where the idea is simply we use something like quadrature and finite elements. We use the nodes themselves. We compute their energy. And you have additional points on the inside, and you can actually find a way analytically to minimize the total energy error and to come up with the best way possible to compute the weights of these nodes such that you minimize the energy for arbitrary shapes of your elements. And we do specifically keep the nodes and additional points on the inside, because if we go down to full atomistics, we want the nodes to be in the simulation so that ultimately you're just doing atomistics. I'll show you this in the next slide. And this sampling scheme actually makes perfect sense, because let's assume we use a linear interpolation. If I use a linear interpolation, that means my deformation gradient is constant within each of the elements, right? And if this is the case, that means all the atoms on the inside of an element are deforming in an affine manner. If all the atoms are deforming the same, that means each atom sees exactly the same neighbors. And as a consequence, the energy inside each element is constant. Of course, as you go towards the edges, you start to see the deformation of the neighboring elements, and so the energy changes. And so by doing what we do over here, we actually take this into account. Namely, we have only one sampling side, a quadrature atom on the inside, which senses the energy of all the points on the inside. And then we have additional ones on the nodes, which feel what's happening on the nodes. Now, of course, you can argue near the edges, you also see differences. So why not introduce a second-order scheme, which has additional quadrature points on the actual faces of the elements? And by doing this, we take into account the constant energy of the inside, the changes on the faces and on the nodes. And by the way, this also works beautifully for surfaces, because if you have a free surface, you're putting one sampling quadrature type atom on the surface, so actually feel the surface interaction as well. And finally, if this is your element, you have something on the inside, you have the nodes. If I refine this down to full atomistics, I just recover full atomistics automatically. I have my three atoms, and they are the ones that carry the energy and have degrees of freedom and so forth. So it's completely seamless. So this is what I showed you before. These are the forces that we saw that were problematic. These are the two new schemes that we introduced. You can still see some tiny forces around the atomistic region, but they're really small compared to what was there before, and we can actually even quantify what they are, and they're bounded. So this works beautifully. Now, let me show you why we did this specific seamless scheme. The beauty here is I never introduced any interface between atomistics and the continuum. It's not that I'm patching two methods together, but it works beautifully for atomistics and the continuum. So for example, if you look at Nano Notation, the top shows us indentation with a pyramidal Berkovich indenter. As the indenter comes in, we see how the mesh automatically refines. I simply tell the code, if the energy is too high, if central symmetry is too high, if the deformation is too high, go and refine and add additional atoms. At the bottom we see the same for a spherical indenter. And so you can start with the most coarse mesh you want. The minute that you localize, the minute that you create dislocations that are running through the crystal, the mesh automatically refines, it recovers those dislocations, and you ensure that while you're running this with the efficiency of a continuum scale, you can still track down each and every dislocation, and each and every dislocation is modeled atomistically. So we don't have to introduce any continuum representation of those defects. And the fourth ingredient that I had on my slide is finite temperature and dynamics. That's generally, of course, not an issue for finite elements. Finite elements, you just make your material parameters temperature dependent, or you couple it to the heat equation. In atomistics, unfortunately, temperature and dynamics are a big issue because it's not a parameter. It means vibration of your atoms. And so I'm not going to go into much detail here. I'm just going to point out that there's ways to do that. The approach that we're normally adopting is the one that was proposed by Michael Ortiz, Yash Kulkarni, Gabriele Venturini, and others, who showed that we can replace our potential energy by an effective potential energy, which depends on the temperature. And in particular, each atom or each wrap atom is now given not only positions and motion, but it's also given a temperature and a vibrational frequency as degrees of freedom. We have to solve for those as additional variables. If you're interested, I saw that Pilar Ariza is giving a talk on exactly this method tomorrow afternoon. So if you have any questions, I think she's even the more appropriate person to talk to than me. This is how we attack dynamics and temperature. And finally, once we've set this all up, we have to solve any problem we're interested in. If you want to do quasi-statics or low temperature, we simply equilibrate the system. We don't use Newton-Raphson or anything like this because the system is simply too big. We have to use an explicit solver. So what we use is called FIRE, which is the Fast Inertial Relaxation Engine by Eric Bitzek and others, which is an explicit relaxation scheme, works pretty much like conjugate gradient but much faster. And if we do dynamics, we can actually solve implicit dynamics here. We use, again, the solver, but by doing implicit dynamics, we can go to bigger time scales. So we're not necessarily tied to the very small time steps that you normally have in atomistics. And so all of these 4 steps, 1, 2, 3, 4, is what we use in order to go to bigger scales. First, we get rid of many degrees of freedom, so we only keep a few degrees of freedom where we need them. Second, we don't compute the energy of every atom, but we pick our favorites. I presented this new sampling scheme that works well. On top of this, we use automatic adaptation. So nobody has to know where atomistics is needed. The code will find out itself as it runs the simulation. And finally, we can also do this at finite temperature, and we can run dynamic simulations at bigger scales than what's normally feasible by atomistics. So now I'm going to show you a few examples of where this is helpful. The first one is I'll point out some size artifacts that we normally get from atomistics where we have to be really careful about, and this is not necessarily an atomistic feature, it's anything that we observe when we do representative unit cells. The second, I'm going to show you some examples of extrinsic size effects and then point out what can be done in terms of polycrystals. So first, this is a very simple scenario, but I'd just like to illustrate one feature that we have to be very, very aware of, and that is, let's say you're interested in void growth or in general, defect nucleation around voids. And many of us are interested in this because this is the precursor to ductile failure. It's interesting for spall strength of metals and so forth. So what you normally do is you create a nanovoid. This is a few nanometers in size. You put it in a box, and you pull on it, or you hydrostatically expand it. Now, what boundary conditions do you apply? You could apply affine boundary conditions. That means we know the response is going to be too stiff. You could apply traction boundary conditions. That means we know it's going to be too soft. So what people normally do is use periodic boundary conditions as an optimum somewhere in the middle, as a compromise. The problem with periodic boundary conditions is that you have to be very careful about the size of the cell that you're using, because ultimately, if your cell is too small, you don't really simulate an individual void or defect, but you're simulating a periodic array of voids, and each void fields its neighbors. That's exactly what you see down here. This is a nanovoid in a very small cell, and I'm increasing the strain at which I'm loading the unit cell. And a strain of 4.2%, you see dislocation loops emanating, and they grow, and they keep growing, and they do funny things. This is the same simulation with a slightly bigger unit cell, and this is the same simulation with an even bigger unit cell. And you can see that the first nucleation of dislocation loops coming out of the void is significantly delayed by the fact that we're using a bigger unit cell. Simply, the void is not feeling its neighbors anymore, and so the apparent response is different. And then finally, once it has nucleated, in the bigger cells, they can also grow and move much faster than before, which is not happening down here. And then again, periodicity kicks in. So whenever we run these simulations, we have to be very, very aware of the fact that the cell size plays a crucial role, and we have to be on the bigger side in order to get the accurate response of dilute voids. Otherwise, you're just computing a periodic array, a grid of voids. And so this is what it looks like in the stress-strain response. Of course, this goes to very high strains, but this is loading in a single crystal environment, so one may expect that. So if you look at stress versus strain with the different sizes, and we tried very many different ones, we can see very different response versus locations nucleating here versus there. So there is a significant delay in the different unit cells. The beauty of the QC method that I showed you before is that I don't really have to care about the cell size at all. What I do is I place the void at the center, I have atomistics around it, and then I coerce them as dramatically as I want. And so by doing this very aggressively, in principle, I could make the cell a kilometer by a kilometer by a kilometer in size. I can still do it on my laptop because I'm simply coercing. But I don't have to apply boundary conditions right here. I apply them remotely, so they don't matter. And by the way, this, of course, was not first discovered by us. These image forces and periodic boundary conditions are very well known. Bill Curtin and co-workers, for example, showed very similar effects for dislocations. One has to be very careful about the cell size again. So this was just one example of voids and where this is useful. This is an example of nano indentation that many people use in plasticity to identify material parameters. And this is a scenario where within atomistics we punch with a spherical indenter into the solid. We can see how a dislocation loop is created. Dislocation loops grow, they interact, and you can see interesting things happening. This is the corresponding load versus displacement curve for a small indenter, for bigger indenters. And we can really go to sizes here which are beyond what you can normally do with MD. Indenter sizes on the order of hundreds of nanometers is only possible if we have atomistic resolution around the indent, but we keep our cores meshed down here. That's the only way how we can go to these big sizes. Otherwise, we could never do this computationally, but it's relevant because this is the realm where experiments are. If you go to your favorite experimentalist and say, please do nano notation with a 0.5 nanometer indenter, they're just going to laugh at you and send you home. But that's just not possible. You can do the same with a Berkovich indenter or with any pyramidal indenter. This is just one example. You can see the beautiful dislocation loops coming out of it. Because this shape is self-similar, there is no size effect. But for example, if you vary the angle, the geometry, you can see very well the impact, and this agrees well with what's generally seen experimentally. And again, we can go to much bigger scales. A few hundreds of nanometers is easily possible, and unfortunately we're not at UT Austin. Our computer is much, much smaller, and we can still run this overnight because of the increased efficiency. So one more example. This is a thin plate with a hole, and I'm pulling on this. In continuum mechanics, that's a very classical problem. Elasticity, actually, we do this in undergraduate or graduate mechanics. If you do elastoplasticity, it becomes a bit more complex, but it's still very simple. We know there's a stress concentration around the hole. We have plane strain versus plane stress across the thickness. And in principle, this is self-similar, so size doesn't matter. If you do atomistics, however, of course the size matters. If you use a small hole versus a large hole, you feel individual atoms. This is zoom in on the surface, and so you do see very strong and very clear size effects, generally with smaller being stronger. The only way we can run these simulations efficiently is because we have full atomistic resolution around the core, at least at the beginning, and we coarse dramatically away from the hole. Again, this can be done adaptively, so as dislocations run, you can adaptively refine. And also, because we use this special summation rule, the surfaces are accounted for, which means this simulation actually feels that there is a free surface. In atomistics, that matters because you have surface relaxation effects. The surface has a different elastic modulus than the inside, and that's automatically accounted for by having these quadrature atoms on the surface that feel the difference in energy. Again, this is what the dislocation loops look like. We start with the hole. This is color-coded by centrosymmetry. Then you can see the loops running away from the hole, for the smaller one happening later than for the bigger one. And they look a little funny, but that's only because you have a thin plate. So you don't see perfect loops, but these loops have to end on the surface, and they're pinned. And that's why you see these intricate dislocation structures appear. If you look at the stress-strain or first displacement curve, it looks generally like this, first elastic, then inelastic behavior. And you can see that the biggest hole shows plastic loading and dislocation onset very early on, whereas the bigger holes just behave elastically for a long time before they eventually start to show dislocation activity. So again, that's a size effect we can beautifully capture. And the last point I'd like to make is, this is still work in progress, but we can also look at grain boundaries. And of course, we know all metals, or most engineering metals, are polycrystals. And so there's a lot going on at the grain boundaries. In general, if you're at the bigger scales, this might not be feasible because we have many defects within grains. We have dislocation-based plasticity. But if you go to smaller scales, say nanocrystalline solids, we know that a lot of the plastic mechanisms are concentrated on the boundaries. There's grain boundary sliding, grain boundary rotation, and so forth. In this case, there's not much of dislocation-mediated plasticity. And so you could consider a scenario where you have full atomistics near the grain boundary, you coarse dramatically on the inside to speed up your calculations. Or, even simpler put, you can also do calculation on representative unit cells. Let's say you want a continuum model and you need to know what the grain boundary energy is. In this case, we can easily set up a unit cell which has a grain boundary at the center. This here is a simple sigma 3 boundary, one grain at the top, the other grain at the bottom. But we don't need full atomistics for this. We are readily coarsened up here, so it's much more efficient than running this with atomistics. And that allows us to do, in principle, arbitrary grain boundary misorientations. Of course, this is easily done for coincidence side lattices, but if you have a very complex grain boundary that requires you to have a huge unit cell, this can easily and efficiently be done in this context. And so, perfectly on time. I'd like to conclude that I try to show you how we can bridge across scales from atomistics to the mesoscales to the continuum. The first step is spatial coarse graining, and we adopted the QC approximation. The second step was to efficiently speed up calculations by using quadrature type rules. The third step was automatic mesh adaptation. That's a very nice way that we can do here because we don't have an interface between the two regions. The fourth, I briefly mentioned, was dynamics temperature. We have seen some interesting results for selected examples. We see elastic plastic size effects. Free surfaces are accounted for. And as I mentioned, it avoids truncation effects of your unit cells. So you can easily do very big calculations without boundary effects. And the last point I'd like to make is that for those of you interested in truss structures, of course, this method is not necessarily limited to atomistics. What if I replace my atomistic potential by the interaction between nodes in a truss framework? So this up here is a truss framework. I work a lot with Julia Greer at Caltech, who fabricates these nano microlattices. And it's interesting to see how they behave under failure, for example, in three-point bending. If you wanted to model each and every truss, each and every beam, that would be extremely expensive for doing it in 3D with millions of trusses. If I know what the interaction between those is, if it's elastic, it's simple. If it's plastic, I can use variation constitutive updates. If I describe the truss interaction by such a potential, I can just throw out my interatomic potential. I use this instead, and I can run beautiful truss simulations of gigantic truss structures, but I only compute it based on a few representative nodes, and that's much more efficient. So if you're interested, of course, I'll be happy to answer questions. Otherwise, you can find information in those references down here. With this, I've come to the end. I just let this up here running. This is a visualization of what the remeshing in 3D looks like. But I thank you very much for your attention. I'll be very happy to take any comments or questions. Thank you.
Very nice. Thank you. Kochmann. Okay. One question, please.
There's one down here.
We already have it.
Yes?
Do you consider that dislocation plus reward interactions with other dislocations?
Oh, absolutely. So when you run atomistics, it's not discrete dislocation dynamics. So I don't even discretize a dislocation itself. If I run atomistics, I only consider the atomic motion. So if a dislocation comes moving in a particular direction, there's other dislocations around. They will naturally interact. They will certainly do, of course. That is accounted for. Of course. Sure. If you're interested in that, I'll be happy to run calculations. We can talk about that. But in principle, anything that you can do with atomistics, you can do with this as well, just at reduced costs.
Okay, thank you. I think I'd like to thank Professor Kochmann and
Thank
together all the other three speakers that really brought on this excellent. And I think that was a great start for the conference. Now we will break for coffee, and as been announced, we will resume again. We'll start again the parallel sessions at 5 o'clock. All sessions are in the building next door, so please check for your chairs. They're in the web. And after the sessions, we'll have the reception outside in the small garden outside. Okay, so we'll see you there. That was great. Thanks very much. Oh, no. It's a nice audience, you see?
Yeah, no, they're very nice.
You saw that there's a very specialized